Hello, this is Dr. Embody. Today we're going to take a look at using dictionaries in an example. And the example we're going to look at is Benford's law. Benford's law is kind of neat because it looks at the distribution of the first digits of a set of data, and there's an interesting pattern. It doesn't work for all data, but it works for a lot of data. So what happens is we are looking at the distribution of first digits in a set of data. And it turns out that the number of ones will be roughly 30% of the first digits. The number 2 will be roughly 18% of the digits, and so on down to number 9, the digit number 9, which makes up about 5%. So what we're going to do is we're going to write a program that's going to try and basically test this theory out. We'll take a set of data and see if the first digits, in fact, meet that criteria. And what I've done is I've grabbed the populations of the countries of the world and put them into a file. So the first one here is China, and then India, and so on. And we're going to look at the first digits in the file, the 1, 1, 3, 2. And you can see there's a lot of ones there. All right? And there's a 9. So what we want to do is count those up and see if we end up with a distribution. So how do we go about doing this? Well, what we'll do is we'll make 9 counters. We'll count the 1s, count the 2s, count the 3s, and so on. And then once we get and we'll keep track of how many digits we read. And so we'll take something like the 1 count and divide it by the total, and that will give us the count of the 1s. And then we'll take the 2 count, divide it by the total, and that'll give us a percentage of 2s, and so on. And then we'll see whether they come out to be 30%, 18%, and so on down. And how are we going to do this? Well, each counter will be in a dictionary. So we'll have a key value of the digit 1, key value of the digit 2, and the digit 3, and so on. So this is very similar to the counting of words such as we did in the text with, say, the Gettysburg Address. What's different here, and that we get to take advantage of, is that we know exactly how many counters ahead of time they're going to be. We've got 9 of them. So we'll set up a dictionary with 9 counters, start them at 0, and then we'll go to our file and we'll just start reading lines in the file and looking at the first digits in each one. Now we do have a couple of things to watch out for. We do have a blank line in there, and the word population is on the top. So we got to handle a couple of things. So there's another blank line in there. So we've got some things like that to deal with. So let's call it the digit counts, and we can use a comprehension. So we'll get a bunch of digits, each one with a counters that named with a digit, and each one will start initially with a value of 0 for D in the string 1, 2, 3, 4, 5, 6. Notice that there is no 0 there, right? And let's take a look at that. So we see that we have we have a counter for each one. Remembering dictionaries are not ordered. So for each digit we have a counter, and its value is 0. And I've already preloaded a couple of things in here. At the top is the Benford distribution. So the 1s have 30%, 2s are 17.6%, and so on down. And we'll use that for comparison later on. It's in a file called populationdata.txt, and now we've created the counters. And what do we do next? Well, now we have to read our file. And let's take out carriage returns and things like that. Now, I have to account, remember we in our file we had a header and we've got some blank lines in there. We need to take care of those. And we can say if line. Remember, if a string is empty, it will be false. If there's something in it, it will be true. So we only want to consider lines that have something in them. So if there's something in them and the first one, the first character is a digit, then we want to collect that. So let's call it the first digit, and we'll put that in our dictionary. So what have I done here? I'm reading in a line, taking off the carriage returns and things like that. I first check to make sure there's something in the line. Then I look at the very first character, check to see if it's a digit, and I assign that first character the name first digit. Then I use my dictionary, which we name digit counts, and for whatever type of digit that is. So if I read the digit 1, then I will be adding 1 to the digit counter accessed with first digit. So that would be, so if the first character is 1, that'll be digits count of the digit 1, and we'll add 1 to it. If it's a 7, then we'll add it to the 7's counter, and so on. So that will build a counter of counts. Now, since we want to do a percent, I have to keep track of the total. At this point, I have collected everything into the counters, and to make the percents, we would like to print them out in order, so let's put them into a list. We'll put tuples in this list, and we will have our digit. Take each count and divide it by the total, so we get a percent. And this will be for every digit and count in my digit count. Right, remember when we have the dot items, that gives us both the key and the value. That will create a list, but what I'd like to do is have that list sorted. Let's take that and call the sorted function. So now I've created a list of tuples, and I'm going to sort it. And I'm going to do one other thing too. My digit, which is a single character, later on I'm going to use that as an index. So let's convert it into an int. What have I done? I've gone through the whole dictionary. I've grabbed each digit and its associated count, and then I'm making a tuple. There's the parentheses for the tuple. The first item is taking that digit and making it into an int. So we have the digit as an integer, and then I have my percent, the count for that particular digit and its total. So I make a whole list of those, and then I'm going to sort it on the first item in each tuple, which would be the digit. So now I will have a sorted list of percentages. And let's give that a try. The list that I have here is called percents. And now let's check it out. So we can see here that the ones have are there 26% of the time. That's pretty close to the 30. The twos are at 18%. Threes are at 12.5%, and so on down. We see that the nines are at 4.5%. So that looks pretty close to what we had, that we were expecting. Let's see if we can make this a little cleaner. So I start off, I have a little heading, and then for each of the percents, remember that's a tuple, so I'll grab a digit and its percent, format it nicely. I multiply by 100, right? Because I've got my decimal, and I want to make it into a percent. I got to multiply by 100, of course. And then I'm going to go back to my original Benford list, and and then grab each of these for comparison. Now, remember, the first one, that's in position 0. So for digit 1, I have to subtract 1 to get the correct number out of my Benford list. Let's try this out. Now we can take a look at our results, and we see we have a population that we found was 26% ones when Benford predicted 30. The digit 2s were exactly the same, digit 3s were the same, and so on down. And you can see that the numbers match up amazingly well.